Hi, this is Trian Lin, and this spotlight talk will be focusing on the topic of test suite minimization for mutation testing of web service BPEL compositions. This paper presented integer linear programming as an exact technique to minimize test suite based on mutation coverage for web service BPEL compositions, which is an OASIS standard for web service compositions. Despite the fact that web service compositions are relatively small, their execution can be very expensive because the deployment and the execution of web services and the underlying infrastructure are not trivial. Therefore, although test suites for the compositions themselves are usually small, it is important to reduce their size as much as possible and without losing coverage. Moreover, solution of test suite minimization can not only reduce the cost of mutation testing, but can also precisely assess the quality of existing test suites. So, what is Web Service BPEL? Web Service BPEL is the OASIS standard for web service composition and also an XML-based programming language describing the behavior of business processes and how they interact with other web services. And what is mutation test? Mutation testing is a testing technique based on fault injection. For example, if a program contains the expression of x plus y plus z, and there's a mutation operator available to replace the operator plus by the operator minus, the mutant contains the expression of x minus y plus z and x plus y minus z can be produced. To minimize the test suite for mutation test of web service BPEL, the paper applied the integer linear programming with two metrics. The first one is to find the smallest test suite number, which gives the smallest mutation coverage, which is measure of the number of mutants killed by the test suite. The second one is to find the smallest test suite number, which makes the smallest execution cost. M here is the mutant, so what's EIJ and CIJ here? This is how this approach mathematically operated. EIJ is from execution matrix E, and the CIJ is from cost matrix C. According to the definition of execution matrix, EIJ is equal to 2 when the mutant MI can't properly execute. Otherwise, EIJ is equal to 1 when the mutant MI killed by the test case TJ, else EIJ is equal to 0. And the CIJ is simply defined as the execution time of mutant MI against the test case TJ, corresponding to invalid mutants are removed from both E and C. Therefore, the result can be assumed that E is a binary matrix and that the times in C corresponding to valid executions. The paper provided the experimental results table as following, where LOC stands for the number of lines of web service BPEL code. I is the set of invalid mutants. M is the set of valid mutants. D is the set of dead mutants. T is the original test suite. And R is the reduced test suite. The last two columns represent the time needed to compute R from execution matrix E, and the reduction stands for the percentage of reduction obtained in the size of the test suites. From my personal point of view, This paper provided the clear concept on why it is important to minimize the size of the test suite, although the test suite is already relatively small. And this paper provides detailed minimization process for two different metrics. This paper also provides experimental result and analysis on it. What's more, it also provides source code repository. Well, I think this paper can be improved more by giving an explanation table of all keywords and the variables, because it is hard for me to read when I find some variable or keywords never mentioned before, but I can find the definition of them in the next following two paragraphs. And that's all. Thank you for your patience and thank you for watching this video.